There are 8 million YouTube talks online, but if you want to really experience it, you have to come in person. It's great. I mean, you'll just meet such cool people.
Hello, and thank you for inviting us to present here at CppCon on this beautiful sunny Colorado day. We are a team composed of Christina Peterson, Zachary Painter, and myself, Victor Cook. And we are at UCF, the University of Central Florida, where we work in the asynchronous and concurrent systems lab of Dr. Damien Dechev. Our application areas are high-performance computing, blockchain, and, as you'll see in this presentation, theory and algorithms for concurrent programming. Fun fact, Dr. Dechev is a PhD graduate of Texas A&M University, where he studied under Bjarne Stroustrup. So, with that introduction, we'll go into our presentation, design and implementation of highly scalable, quantifiable data structures in C++. So here's the overview, and we're going to start with why we did what we did, and then we'll talk about exactly what is the definition of quantifiability, and then we'll go into some detail about how to use it in a real program in C++. The first section will be motivation, and we'll go into that now. First, let's consider correctness conditions, which have been around for some time, 3 or 4 decades, as a way of defining the correct behavior of multiprocessor programs. Serializability is one, sequential consistency, quiescent consistency, and linearizability. They all have something in common. They require reduction to a sequential history. And in the beginning, with 2 or 3 processors, maybe 4 if you were at a very expensive computing laboratory, then that wasn't such a big deal. But today, with machines that are under $10,000 with 64 threads operating very quickly, it turns out that in less than a millisecond, you can have more combinations of method calls than there exist atoms in the universe. And so it makes the analysis very complex. The standard for correctness these days is linearizability, credited to Herlihy. Herlihy came up with this in 1990, along with Jeanette Wing. And this was back in the days of abstract data types. And as I mentioned, only a couple of processors. So it was a great contribution at the time. And it defines a correctness as such. A concurrent history of method calls is equivalent to a sequential history. That's that mapping we were talking about. And then each method call must appear to take effect at some instant between its invocation and its response. Now that sounds pretty obvious, right? It would not take effect outside of the invocation and the response. But the problem is that it doesn't really say enough. Even though it claims now to be a real-time ordering, which in some sense it is, it doesn't give you enough detail. It's kind of like you are very concerned about what happens inside of a restaurant, your whole process being a restaurant, if a restaurant were a CPU. And so you make sure that everyone gets served food sometime between the time when they get in line at the door and when they leave. Okay, but that's not enough. So we have some practical concerns today about linearizability. Method calls are not conserved. In other words, some people might not get any food at all. Timing is critical to correctness, as we'll see, but it can only be estimated by applications. Applications don't control the OS. They don't really have control over the timing in most cases. The intermediate state, that's what's happening inside the restaurant, is opaque. And in computer science terms, it's denotational, looking at the result, rather than small step operational where you can track each step. The correctness is binary. This is a big problem because there's no metric for engineering trade-offs. You can't tell whether one algorithm is better than another if they're both correct. or the same if they're both slightly incorrect or very incorrect. That's hard to tell too. And the other thing is a very subtle point, but important. You're forced to make assumptions about how abstract data types are defined and the semantics of objects in order for linearizability to be really useful. i.e., for instance, people allow pops on empty stacks all the time. That's not really strictly correct according to abstract data types. It also limits parallel computation to this outdated serial model. Now we're going to get down into the weeds here. We're going to look at what are called concurrent histories. And these are the building blocks for correctness proofs. And we'll see this first objection, how correctness depends upon timing. This history is not linearizable. And it's because there's no overlap between that that push of 7 and that push of 8. If there were, then it would be ambiguous as to whether 7 or 8 were at the top of the stack, and then the pop of 7 would be okay. But it's not. And that interval might be just a nanosecond or two. And how do you measure that? Well, it's pretty hard. Here we have the violation of type constraints and atomicity that's caused by the conditional pop. The conditional pop must be assumed here in order to make this history linearizable. There's no other way to make a valid path without saying that you could throw out that a pop of 7, because there is no 7 before you get to the push of 7. On the other hand, you can see that it's definitely serializable in all cases. You can always match the push up with the pop if it's a database or if it's a serializable condition. Likewise, it's quantifiably correct, but it's only linearizable in this case. We have a yes there, but it's only because of that conditional pop. The conditional pop has some problems. It's inherently unfair. If you had a kind of rhythmic timing between the processes, you could easily end up with a situation where there's starvation, and this P0, even though it keeps trying, would never overlap the time when there is something that can be popped off there. Let's say it's a resource that they need, or could be a lot of things representing not just a stack. We're talking about stacks here because it's kind of an abstract data type, but it could represent a lot of things. Then finally, you have an objection from just a practical consideration that most of the time we want to match things up. We want things to work. We want to build transactions. We don't want to throw things out just because they're a few microseconds off in timing. And so, here's a case where logically we want to match the pops up with the pushes and we create correctness. But in this case, linearizability says, no, you can't do that. So given all these kind of micro details, let's look at the bigger picture for a minute. What are the drivers we have for change? First, as we all know, Moore's law is not what it used to be. And so architectural demands are that we use these multi-core resources better. We have a general acceptance now also of relaxed semantics. And the relaxed semantics means you're going to kind of ease off these correctness conditions a little bit in order to get performance. The complexity we talked about of combinatorial models is, and the model checking of those is intractable. And there's a bigger demand as well in all kinds of distributed and concurrent applications. So here is what we want. Here's our desiderata. We want a native correctness condition. It doesn't rely on a sequential history. That way we can throw out all that combinatorics. We want the timing and the semantics in the type system where the application can see it. You don't want it to be something opaque in the operating system. You want it to be defined operationally so you can track it step by step, not just at the end after you look at the combinations of results. And you want it to be compositional so you can build big systems out of little systems, and also free of bad things like inherent locking and weighting. Now, linearizability does have the second too. We got to give credit to that. And 30 years ago, it was a big achievement to get that. So now, if you look at, again, getting a little even more theoretical and more big picture, we want to look at first principles. We don't want to look at just the modifiers on the first principles. We want to look at the code. We want to see the code actually says this has to happen. It can't just be thrown out. We're going line by line. We're debugging a program. And it's kind of like we want to see what actually happens Then we worry later about modifiers upon them. And so this is just a little bit of inspiration by Descartes. And you'll see later, as we define the model, how really Descartes is important, because we also use a lot of linear algebra in our models. All right, so now I'm going to hand it over to Christina, and she'll tell us what time it is.
All right. Hi, I'm Christina Peterson, and I'm going to be introducing quantifiability. This is our new proposed correctness condition, and it embodies two main principles. The first is that the method calls are conserved. This means that the method calls are considered first-class objects, and they must succeed, remain pending, or be explicitly canceled. So even pending method calls are first-class citizens. We don't just throw out method calls when they reach an undefined state of the data structure. And also, the method calls count. Every method call makes an impact to that system state, and our philosophy is that we can measure that impact for the purpose of verifying correctness. So the definition, the informal definition of quantifiability, is that a history is quantifiable if each method call succeeds or remains pending or is explicitly canceled. So here we expect that the method calls are all first-class citizens, and if they reach an undefined state of the data structure, they will be stored in that data structure to be filled later. Also, the effects of the method calls appear to execute atomically and in isolation. So this is a baseline correctness property required by all correctness conditions. And then the effect of every completed method call makes a measurable contribution to the system state. So here's where quantifiability falls within the reference to other correctness conditions. We have serializability as the broadest correctness condition, and linearizability is the most restrictive. Sequential consistency and guessing consistency are not comparable, but they do both encompass linearizability. Now, there's a section underneath quantifiability that is none of those correctness conditions are quantifiable, and that's if the method calls are not conserved. So the beauty of measuring the impact of method calls on the system state is that we can verify, and we do this verification in vector space. So our vector space spans 4 different dimensions. These dimensions include methods, processes, objects, and items. So the methods are the functions that either access or manipulate the concurrent objects. The processes are the actors that invoke those methods on the concurrent objects. And the objects are the containers of the concurrent system. The items are the data that contains the data that are passed as either arguments to the method calls or returned from the method calls. So we represent our concurrent histories in vector space. And the way that we do this is by creating a basis vector. This basis vector includes all possible values of those dimensions. So to the left, we have history h1. And the possible values for the method calls are push or pop. And then for the threads, we have p0 and p1. We have x, which is our object, and the item is 7 or 8. So now we want to define what is happening in the history. So we look at h1. So the first method is x, push 7 onto x by p0. That corresponds with the first position of the basis vector. And so we set that to 1. Then the next method call is push 8 by process p1. So that's going to correspond to the 4th position of that basis vector, and we set that to 1. And then finally, we have pop 7. That corresponds to the 5th position of the basis vector. We set that to -1. So now we have we have to define how we assign those values. And we do this by, the history vector is going to be updated on as every method call is encountered in the system. And so we're going to set hprev to be that previous state of the history vector. Now, if the method call is a consumer, we're going to add 1 to that position in the basis vector that corresponds to that producer. If the method call is a consumer, we're going to subtract 1 from that position in the basis vector. Now, the idea is that we want to be able to add up the values. And if anything is happening that isn't expected, like we're consuming something that doesn't exist, the sum is going to drop below 0. And so now for the readers. So the readers don't change the state, but they do access it. And so the way that we measure this is by the geometric series 1/2 to the j, where j is the jth read. And so we subtract 1/2 to the j, and what happens is as we add up the readers, they're never going to quite reach 1. So if we add that to our producers, then as long as the item exists, we should be greater than or equal to 0. Now for the writers, we're going to, the writer will produce an item, and that's going to overwrite some old item. And so the produce part of that method, we're going to add 1 to that position in the basis vector. And then for the consume, we're going to subtract 1 in that position for the basis vector. So here's an example of a quantifiable history. It's a concurrent map, and XA is a specific key in the map. So we're going to check the correctness based on the granularity of the keys. So here we have either insert, put, or get. And then we have process 0, process 1, key XA, items 7 and 8. And so the first method call is the insert 7. So that corresponds to the first position of that basis vector, so we set it to 1. Now the get is a read, and so we're going to set the second to the last position of that basis vector to -1/2. And then the put is a write. So we're going to write an 8, and then we set that to 1, and then the 7, we're going to overwrite that. So we set that to -1, and that corresponds to the 5th and 6th positions of that basis vector. So now we want to prove that this history is correct. So what we do is we reshape it into a 2x6 matrix, and then we're going to sum across the rows. So the top row corresponds to the item 7, and the bottom row corresponds to item 8. So the first thing we're going to do is we're going to add the producers and the readers. And so when we do this, we get 1/2. So we're greater than or equal to 0, so we're still correct. But what we have to do now is take the ceiling. And what's going to happen is it will be 1 if the item exists, and 0 or less than 1 if the item does not exist. And then we subtract 1 for that consume operation, and we get 0. So that means that 7 does not exist in the final state. So the 8, we just did a put 8, so that's just going to be 1 for the 8. And then we add across the row, and then that's going to be 1. So 8 exists in the data structure in the final state. Since each position of the vector is greater than or equal to 0, then we are quantifiable. So what's the benefit of this? The benefit is that the verification becomes a matrix operation. And so here we're interested in what's the time complexity of this matrix operation. So let n be the total number of method calls in the history. Let I be the number of input-output combinations, and j be the total number of objects. So it takes O of n time to iterate through all those method calls, do the value assignments, and then update the history vector. And then if there's j objects and I different input-output combinations, there's going to be I times j configurations. And so it takes I times j to go through each of those configurations and make sure that we're greater than or equal to 0. So the total time complexity is O of n plus I times j. So what we've done up to this point has been to prove that a single history is correct. But now we're interested in proving that the entire data structure is correct. So we draw inspiration from linearizability. So for linearizability, you can identify a linearization point, which is a single instruction in which the entire method call takes effect. So for quantifiability, what we need is a visibility point. It's a point in which the entire method becomes visible. This preserves the all or nothing property and demonstrates atomicity and isolation. So one of the benefits of quantifiability is that it's compositional. So we can reason about each method call individually, and then the composition of the method calls together will also be quantifiably correct. The next step is to prove method call conservation. And the way we do this is a proof by cases, where a method call, we need to prove that a method call completes its operation on the successful code path. A method call's pending request will be stored in the data structure on the unsuccessful code path, and that the unfulfilled method call will be fulfilled by the corresponding inverse method to make sure that it's correctly handled once that pending method call is fulfilled. So now I'm going to turn it back over to Victor to explain our entropy measurements.
Thank you, Christina. All right, so as most of you probably know, the outcome or the output of a concurrent program is non-deterministic. There are many correct outputs, and there are many incorrect possibilities as well. So there's already disorder. There's already a problem here in terms of every correctness condition, even the most strict, is not going to give you what you think you're going to get, which is one answer. It's always going to be lots of answers. But unfortunately, no one's really been able to quantify that. No one's been able to put a metric on that. And so as our correctness conditions called quantifiability, we took it upon ourselves to do this, partly because we knew that nobody was going to accept a new correctness condition until we were able to show that at least we weren't making things a lot worse than they already are. And so the previous work focused on the relaxed correctness conditions. Problem is that relaxed semantics is really interesting and useful, but it's a technique in programming. It's not a metric. And so we needed to measure what relaxed semantics and the other techniques would do and how correct is the result. And the result is not a binary yes, no. It's going to be, hey, this is pretty good, this is not so good. And as engineers, we want to make things as good as we can, and there are always trade-offs. So the fundamental problem being that the existing metrics are not capable of measuring performance effects of a correctness condition because they don't pay attention to delays. Once you're inside the restaurant, they don't care when you get served the food. So here's an example of another concurrent history, and it's got 3 NQs followed by 3 DQs. Because the NQs all overlap, every correctness condition says this is fine. And all of these, every single one of the combinations is still correct. So, that's an interesting case of everything being correct. But intuitively, we know that some things are more correct than others. If you're the first NQ and you come in a measurable period of time before the second NQ, and which also comes in before the third one, then you know that really what should be happening is that first on the left. The other ones, although they're still technically correct, they're just not as good. So we have to, that's kind of the start of what we did. We looked at the invocation times, and we measured the invocation times on a number of existing benchmarks with correct code. And then we came up with this model. First thing we had to do was kind of some sort of measurement, for instance, of output results that we know are disordered when they should be in some order that we very carefully input them. But how do you measure that? Well, we went back to Knuth, and he had, way back in the 60s and 70s, studied this problem because he was really interested in sorting algorithms. So he wanted his sorting algorithms to be getting inputs that were more or less difficult. And there's a couple of pages in his famous work on this. And he calls it the inversion and the inversion count. And so we started with that. And then we built on the inversion count as a measure, and we realized that we could create a probability mass function out of that and use Shannon entropy to measure the actual entropy of that probability mass function, which was really fortuitous. We have these 2 super famous computer engineers and scientists that we can rely on here. Again, when you're taking a new correctness condition, you don't expect everybody to accept it. I mean, the correctness is correctness. It's kind of like the basis on which we're going to build everything else. So we have to have a lot of grounding there. And so here's what we did. We created that probability mass function, and we were also able to normalize it, which is really good because now not only can we take 2 implementations of the same data structure and decide which one introduces less randomness. And all the time we're kind of thinking that the randomness is a trade-off with performance, because you can get 0 randomness. All you have to do is use only 1 core. So you get 1 core, it's deterministic, it goes back to deterministic, all right? So this is the trade-off. And so and then we also found some things like stacks are really high entropy. Queues, not quite as bad. maps and sets, unless there's a very small number of mappings where you get a lot of collisions, they're much lower entropy. And that's all part of what we could see when we use this normalized entropy. So we're not going to go through all of the different data structures, but we'll look at some stacks here. And then we'll also reproduce the stack in the real-time demonstration later on. And so stacks are, as I mentioned, high entropy. There's this stack that's called the elimination backoff stack, and everybody loves it. And it's one that I studied in my first concurrency class. And it's a really nice piece of code. It's really elegant and beautiful, and it's fast too. And so, but what was great about the entropy thing is that now we know why it's so good. Not only is it fast, but it's also low entropy. And so here we can see 3 stacks. We've got our QStack in blue, and all these 4 diagrams rather, are the same experiment, okay? They're different views of the same experiment. The one in the upper left with all the dots and colors is the raw data. That's like the actual item indexes that were pushed onto the stack and popped off. And then the height of the dot is the inversion count for that particular item using the Knuth inversion. And so that, if you kind of flip it on its side and then add it all up, that's how you get the probability distribution. And that's where you see that band in the middle becomes that that orange mountain on the next diagram. And that indeed is the elimination backoff stack. It's pretty fast and it's really low entropy. And you can see that on the next chart where it's way below on the entropy scale of the other 2. And then finally the performance. It's low entropy, but it's not the best performing thing, but it's pretty good. It's way better than the Treber stack. And ironically, the Treber stack, got to give credit to Treber, we're talking 1987 here. This was even before they had some of these correctness conditions. But it has a lot of contention. And the Treber stack has entropy that's almost as bad as the quantifiable stack, which performs 10 order of magnitude better. And so that's what we're doing here, is we're doing some engineering, and we're accepting the non-determinism that's inherent in the concurrent programs. So we can also here's another case study of engineering trade-offs, and this is a K-FIFO. So we're doing the relaxed semantics here on one axis, the y-axis going up, and then on the x-axis we have the number of threads. So what's interesting and not necessarily obvious, but certainly shown in this heat map, is that the effect of the relaxed semantics is almost equivalent in adding entropy, or i.e. disorder, to the effect of adding threads. So given that, you don't want to be in that upper right-hand corner because there's just a lot of disorder happening. You might as well just pick a value out of a bag at random. And so then you got the next diagram, which is performance. And performance, we're showing it as a cooler color here, and the dark blue is the fastest. You see something that the relaxed semantics is giving you a higher performance. The threads kind of top out here, so you don't get quite the same symmetry as you had in the entropy. And then you overlay the two with a function. Of course, you can choose a function, but we overlaid essentially subtracting one from the other, and then you get this kind of sweet spot here. So this is where you can make engineering trade-offs between the acceptable amount of disorder in your concurrent programs and the performance that you want to achieve. And so with that, I'm going to hand it over to Zach, and he's going to tell you exactly how we did this.
Thank you, Victor. So I'm going to talk about actually designing some of these quantifiable data structures and some of the design decisions we made, and we're going to go into some of these engineering trade-offs that we're able to make while working with this correctness condition. So going back over the quantifiable conditions, what is required? We need to make sure that all method calls are conserved. And since in this case we're designing a stack and a queue, the case that we're looking at there is a pop on an empty stack or queue. Typically that'll return null. And so in order to conserve that, we need a way to make sure that the pop actually always returns something. And we'll talk about how we do that. And then also we need to make sure all methods are atomic. This is pretty standard for pretty much every concurrent data structure. And then a design goal that we have is we want to make sure that we prioritize avoiding contention over resolving it. So resolving contention, this is something that usually occurs when you're using a compare and swap in a concurrent data structure. If two threads attempt to perform an update at the same time using compare and swap, one of them is going to fail, and that's a way of resolving the contention that occurs. But we prefer that doesn't happen in the first place. We'd prefer that every thread just always succeeds in all the updates they try to do. And so that's what we're going to try to prioritize. So first, let's talk about the conservation of method calls. So this is a stack example, and there's 3 different times. We have at the beginning, and then we have time A and time B. At time A, 3 pushes have occurred, and the stack has sort of grown out to have 3 objects stacked up. And then at time B, 5 pops have followed that. So the first 3 pops will reduce the stack to empty, and then the next 2 pops will be occurring on an empty stack. We don't want these pops to return null because that means that they wouldn't be conserved. So what we're actually going to do is we're going to start forming what we call a negative stack, where these pops actually exist as an item in the data structure. And they can actually, incoming pops at any point afterwards would collide with those pops that are the pending pops that are sitting in the data structure and satisfy them, allowing them to actually return a value. And this of course means that the pop essentially happened before, in terms of the real-time order, of course the pop occurred first and then the push came afterwards, but for quantifiability, that's not a problem. That doesn't violate our correctness and quantifiability. So providing atomicity, of course, we're relying on compare and swap. In the C++ atomic library, you're probably familiar with the call there. That's what it looks like. What compare and swap does is it atomically updates an object given an expected value. If the expected value is incorrect, no update occurs. So the way that this is usually used in a concurrent data structure is that a thread will read a memory location that it intends to update, and then it'll do some calculations or figure out what it needs to do based on the value that it reads, and then it'll attempt its update. And it'll attempt its update using compare and swap. And when it does that, it'll pass in the value that it read, and if that value has changed because another thread came in and did an update first, then the compare and swap will not succeed. And so that's the way compare and swap is typically used, and it ensures that any operations that threads are performing are occurring atomically and that they're based on the correct values that were read in the memory location. So with that, let's talk about the quantifiable stack. So typically, in a concurrent stack, what you would see is that threads would, if you have concurrent pushes, so for example, if you have 2 threads trying to push 5 and 3, they would both try, one of them would succeed, one would fail, and then the other one would try again, and you would end up with a stack that looks like what you expect normally, where either 5 or 3 is at the top. In the case of contention in a quantifiable stack, we're actually just going to create a fork. So we're sort of leveraging this, this non-determinism that's already existent in concurrent data structures. And we're just going to create a fork and have both 5 and 3 exist at the same time at the top of the data structure. And at that point, an incoming pop may actually pop 3 or 5. Both would be valid because push and pop can insert or remove at any leaf node. And so we're sort of just pushing the non-determinism into the data structure itself, and that allows us to get a lot of extra performance. So additionally, because of this, to make it easier to check for leaf nodes is something we're going to need to do in the data structure frequently. We maintain the doubly linked stack. And the reason we bring that up is because of the double link between each nodes, a lot of push and pop operations, they actually require an update of multiple pointers. So if you're aware, compare and swap can't update, or a basic compare and swap can't update multiple memory locations at once in an atomic step. So we need a little help to be able to update multiple memory locations at once. And the way we do that is with descriptor objects. So what a descriptor object is it contains all the information necessary for an arbitrary thread to complete its operation. And so here's an example of a descriptor object. For our stack, it's pretty simple. It contains an operation field, and the operations that are available are fork, push, or pop. And then it contains a field that indicates whether it's active or inactive. So let's go into examples. So here's how push actually works in the quantifiable stack. So in order to push a node, a thread updates the node's descriptor pointer using compare and swap. So every node will have a descriptor pointer in it. This is a very common design pattern for concurrent data structures that use descriptors. And if the descriptor pointer is empty or it has an inactive descriptor in it, then a thread may update it. So for a thread to perform a push, they're going to update that descriptor pointer. So in this case, we have a thread attempting to push 2. It's going to add its descriptor to the current top of the stack. And by doing so, it makes its operation visible to all threads. So at that point, any arbitrary thread could actually finish this operation because it has everything it needs. It has everything it needs to understand what the operation is, and it's going to know how to do that. So, so at that point, what would follow is that any thread would complete the operation by, of course, creating the new node and linking it up, updating the top pointer. And the new node that it pushes would also have the descriptor already in there, just because we want to make sure that none of these nodes are touched until the operation is truly complete. As long as the descriptors are in there, no other threads can perform concurrent operations at these nodes. So at this point, we have the operation would be complete once the node is pushed and all the fields are updated. So we would just set the active field in the descriptor to false, and this in one atomic step makes the entire operation complete, and that allows other threads to then go in and start doing whatever operations they want. As for pop, it's pretty similar, except pop requires that we update 2 descriptor pointers right away. So in this case, the thread would update the descriptor pointer on the node at the top of the stack and the node immediately following that node. And for that reason for that is that both of those nodes are going to have fields that need to be updated in order to complete the pop operation. So they both need to have a descriptor in them. But other than that, it's pretty simple. After the descriptor is placed, any thread would then just remove the node at the top of the stack, leaving just its successor, whose descriptor would then be set to inactive, allowing other threads to move forward and complete, in order to move on and perform more operations afterwards. And finally, we have fork. The fork operation is very simple. All that happens is that a descriptor is placed inside the node, and then a thread may go and initialize a new top pointer and point that top pointer at the descriptor, which opens up essentially the branches that we were talking about before, which is going to relieve the contention, allow threads to spread out and perform concurrent pushes together. So obviously, entropy is a big part of this. We're talking about reducing entropy because it'd be possible to create a quantifiable data structure that has just like maximum entropy, and we don't want to do that. We want to make sure that we're doing these trade-offs for performance. We're trading entropy for performance in a smart way. We hopefully want to, so we don't want to maximize our entropy. So the ways we keep entropy down, we can reduce the time between new forks. We can limit the maximum number of branches, but most importantly, what we find is that it's really effective to enforce a maximum height disparity between different branches. So what does that look like? So if we have a stack that's in this state, we see that the left branch has grown a little bit farther out than the right branch. So what happens is when we see this happening, what it means is that the concurrent history that we're getting from this data structure, the history of operations, is going to diverge further away from the sequential deterministic history that you would get running this on one thread. And that increases entropy. So in this case, we have a branch height disparity of 2. We would want to keep the height disparity low. So we don't want one branch getting really far ahead out of the others. We want to keep the pushes that are happening at a similar times on the same level, so that the branches are sort of being built flat layer by layer, and that keeps entropy down. And so it's very simple to just sort of have threads actually check their neighbor branches every time they go to do a push or a pop, and make sure they're not getting too far ahead or too far behind in order to keep these branches flat and keep the entropy low. So as for the quantifiable queue, the implementation, branching doesn't really make sense in a queue because you're producing and consuming from opposite ends. You have a tail pointer and a head pointer. So that branching that we do in the quantifiable stack, you can't really do it. So instead, the quantifiable queue we actually implement as a multi-queue. So it's essentially equivalent to a quantifiable stack that has reached a sort of maximum number of branches, which would occur under a lot of contention, except it starts out that way. And the thing about it is that we can still use this, the height disparity method to keep the entropy low by maintaining that the Q, each of the branches, or the tail pointers, here we have 3 of them, we're gonna make sure that those are always maintaining a similar amount of operations occurring at each point at similar times. So we would track the number of operations occurring at each tail and head pointer and make sure they're relatively equal. And that is how we would minimize the entropy on the Q, though because of this reason, the Q would have a little bit higher entropy than the quantifiable stack. So now we're gonna actually run some code from these data structures, from our implementations, which are open source. Then we'll show the links for those later if you want to go check that out. And we're running these on our lab machine. It's an AMD EPIC. It has 32 physical cores and 64 logical threads. And we're going to load that up and get some performance results. We're going to be comparing it with the Trebor stack and the elimination backoff stack, which earlier you saw the entropy measurements for those data structures, and we saw that the elimination backoff stack actually has a pretty good balance of performance versus entropy. It actually has less entropy than the Trebor stack, despite having higher performance. So we're going to, hopefully we're going to get that up. Okay, so yeah, so the experiment is running here. What we're seeing is at the start, there aren't that many data points, but it'll even out. So we're comparing the QStack, the quantifiable stack, the elimination backoff stack, and the Trebor stack. And we also have another a sort of flavor of the quantifiable stack, which doesn't do any branching. It instead starts out at the maximum number of branches, just like the quantifiable Q. So we sort of, in a really high throughput experiment like this, we'll just gonna sort of embrace the branching scheme and start out with a lot of branches. And drop the overhead of actually managing those forks. So that's what the label in yellow is. It's the quantifiable stack that doesn't actually perform branching. So what we're seeing, of course, is what we expect. The Trebor stack is there at the bottom with the lowest performance. It has a ton of contention. You have, as the number of threads grows on the x-axis there, it's at about 30 now. You're going to have 30 threads all fighting over a single top pointer. And those compare swaps are going to be failing all over the place, and so you don't see any scalability essentially, and it's just that's the kind of thing we're trying to avoid here. The elimination backoff stack does better. It actually has a way to avoid some contention with the elimination array. So in the case of contention, threads actually go into the elimination array, place their object, and you kind of sort of avoid the contention of the top pointer. And then you have both of the QStack versions. We see the regular QStack with branching sort of taking off. It manages to remain scalable because it's actually, you pretty much don't expect to see any scaling in a concurrent stack because of the inherent contingent with the data structure. But with the quantifiable stack, we're actually able to avoid that at the cost of entropy, of course. This is the engineering trade-off we're essentially making here. And it's really, the best case is with the quantifiable stack that doesn't do any branches. We see that it performs by far the best, but at the cost of potentially some increased entropy there. So now that that's complete, I'm going to hand it over to Christina, who has some an example of a vector space demo.
Yes, so I'm going to get that set up right now. Okay. All right. So what I'm going to do is we're going to test the QStack and the QQueue. And so I'm going to run a quick script, and it's going to produce the vector space analysis. And so we're going to look at the QStack first. And so what this tool does is, this tool is actually checking linearizability using the vector space model. But the one thing I had to do to account for real-time ordering was to add a promotion-demotion scheme. And this scheme is also based on the geometric series. So anytime an item is determined to have a lesser priority than another item in the data structure, it needs to be demoted. And that demotion is going to be 1/2 to the j, where j is the jth demotion. And so what we have in the main first matrix is all of our method calls. So the x-axis is the method ID. this method ID is not necessarily the real-time ordering, it's just the ID that was assigned to it. And then in the left column, we have our item. So the green items that are inside of that matrix, those are all of our pushes, and the blue, which is -1, that's going to be our pops. And so the second column is our promotion, demotion. It's all just added up into that column. And then the right-hand column is the final sums. And so we can see that this stack, the final state was 22, 18, 5, 23, 19, 15. So the QStack is based on branching, so it's going to loosely resemble the linearizable order. So at the right, we can see that 1 should be the highest priority, and then all other priorities are going to fall in between. And so in this case, 22 was indeed the highest priority to be removed, followed by 18, and then 5. So you can see that this is actually following very closely to the linearizable order. And if I check through every single item, it probably does. Now, the red means that there was an item that was removed out of order, according to linearizability. And so that's why it dipped negative, which is highlighted in red. So you'll see in the main matrix that there's a couple of back-to-back pushes and then pops, and that's because when a pop tries to pop from an empty stack, it's going to push on a descriptor that says that it wants to push an item. So when a push comes along, it's going to fulfill that pop and immediately pop the element it was going to push. So that's why we see a couple of back-to-back. Now, to check quantifiability, it's quite simple. We just ignore the promotion-demotion column. And so we can visually inspect that every single pop had a corresponding push. And so if we sum across the rows, we're going to be greater than or equal to 0. So this queue is quantifiable. It actually looks like it's also linearizable. So we got some performance benefit there without the cost of too much out of order method calls. So now I'm going to look at the QQueue, and so this one, the QQueue is it usually is even more out of order than the QStack because it uses the local queues. But in this case, it looks like 19 had the highest priority to be removed, so it does follow the linearizable order. But we can see that there was a couple of DQs that happened out of order, and that's what the right-hand column, we see some red highlighted, which indicates that we got some negative sums. Once again, in the main matrix, the back-to-back NQ DQs, that happens when a DQ goes and it tries to DQ from an empty queue, so it puts a descriptor that says that it wants to DQ, and so when an NQ comes, it's going to fulfill that DQ and immediately DQ the item it was going to NQ. So that summarizes the result for our vector space verification. And so I'm just going to pop back into the presentation. And so in conclusion, our key takeaways. Quantifiability, it enables highly scalable data structures by permitting relaxed semantics. And in some cases, we don't even compromise method call ordering too much. Sometimes we're still very close to the linearizable order, but we get that performance benefit. But that doesn't always happen. The second point is that the vector space model enables very efficient verification for checking the correctness of a concurrent history. This is a big improvement over the traditional approaches that use comparison to legal sequential histories. That's actually an NP-complete problem. And so we've reframed the problem to be a polynomial time problem. And then finally, entropy provides designers with the ability to assess the trade-off between correctness and performance for choosing the right correctness condition for their data structure. And our source code is available. The QStack and QQueue are available at Victor's GitHub under the quantifiable branch. And then for my vector space verification, that's under my GitHub handle in the vector space repository under the GNU plots branch to be able to plot the visualization. And so that concludes our presentation. Are there any questions?
I guess I'll break the ice here. So I have a situation where I happen to know that I care not at all about entropy and only concurrent throughput. What would be the best data structure for that?
Well, if you don't care at all about entropy, then you definitely would want something that resembles more the quantifiable stack or queue, because that's going to give you, so in the case of like, a stack or queue, that's going to be the only data structures where you can get some real scalability out of that. Of course, not caring at all about entropy is kind of a slippery slope. But yeah, I mean, to answer your question, yeah, if you don't care all about entropy, you definitely want the quantifiable stack or queue. That's going to give you by far the best performance.
Right. And I guess the lead on to that is, are there, assuming I started with a quantifiable stack as my data structure, are there optimizations that I could make based on it when I know I don't care about entropy and I'm willing to do that even further?
Yes, yeah, essentially. So not caring about the branch height disparity, things like that. Anything that you do that makes it so that a thread is able to just work constantly, it's not failing its compare and swaps, and it's just getting a lot of operations pushed through successfully without stepping on the toes of other threads. That's going to increase performance, but potentially increase entropy as well.
Cool, thanks.
So I was wondering to myself, when does this measure of how correct you are actually matter? And the one thing I came up with is, well, when you care about like fairness of latency, for example, of a bunch of clients. But I suppose that you guys probably have a bunch of other examples, and so I'd like to hear.
Yeah, so when does it matter? You can look at, this diagram here in the lower right, which is kind of similar to very similar actually to the results that we presented live. And you'll see that there's a crossover where the overhead that's involved with the descriptor objects and some of the height checking and so on that Zach described, for a while it's too much overhead, and actually the quantifiable stacks are slower. But at around 10, 12 threads, it just starts to go up and it never stops, where the other ones are pretty much reaching a point where they can't get any higher. So it really matters on how many threads you have, the answer to your question.
I'm not sure you're answering the question I thought I was trying to ask.
Okay.
So like you said earlier, in principle, all of the orderings are correct, but there's some notion of, like, intuitively, some things are more correct than others. Mm-hmm. And I'm wondering when being more correct matters.
Yeah, that's application dependent. And as the other gentleman over there said, he didn't care about entropy. That's one application, but other applications, and it matters in different ways too, because sometimes the ordering doesn't matter, but the clumping together matters. And that's another reason why that elimination backoff stack is so good. Like, imagine if you had four wheels in an electric car and you're hitting the brakes. The fact that you might be a millisecond later isn't going to matter a lot to the human driver, but what you really want are the wheels to all go at the same time. Or if you're doing anti-lock, you want it to be pumping, alternately in such a way that the car doesn't skid. So that kind of stuff is application dependent, and it really needs to be opened up, that whole box, and that's what we're trying to do here.
Well, first, thank you for the great talk. It's actually very interesting. My question is, do you have any other data beyond the micro benchmark? Because sometimes when you see some improvement from the micro benchmark, it may not, be reflective on real world use cases or large scale parallel workloads.
Yeah, we did focus on these micro benchmarks, and in the papers we talk about the Synchrobench benchmark as one of them, and we were able to establish this point of the entropy trade-off, as well as the fact that you can compare with normalized entropy. You compare the different data structures. Some data structures just don't have a lot of entropy, and they're going to run fine. And so, to answer your question about when, it's kind of similar to the when does it matter question. Is that as you scale up the system, quantifiability does provide the composability that'll let you rely on the components behaving and then the overall system behaving in a similar way. But it's not always the case that it's really important. Like the stack may be a very small part of the overall system, and then it's not worth going into a whole nother kind of correctness condition or way of thinking about programming to improve your performance when the parallel part is not important. But if the parallel part is important, and especially if there are a lot of threads, that's when you really need it.
Sorry, can I have a follow-up question?
Sure.
So it looks like this kind of entropy can be very useful, especially when you have a lot of thread. And have you ever looked into like GPU computing or this kind of data parallelism, which might be very helpful?
Oh, Zach, you want to talk about that?
That's a really good idea. We haven't done that yet, no.
Thank you.
Hi. Is it my turn?
Go ahead.
Okay.
Yes.
I thought the descriptor technique was really interesting. I'd never seen that before. It sort of reminded me of like journaling file systems, how you kind of like write what you're doing before you do it. So I had two questions about that. One is that a new technique, or is that something that had a lot of prior art? And the second one is, how do you handle the memory allocation of those? Do you have to allocate memory to do that, or do you kind of have a fixed pool of them, or do you just need a fixed number for the whole data structure?
So the use of descriptors is a common technique in a lot of like lock-free programming and stuff. So that's not a new something that's new or unique to quantifiable data structures. As for the memory allocation in concurrent programs is sort of a problem, its own problem space. For our benchmarks, we do sidestep that problem just with pre-allocation. But of course, in like a real system, there are hazard pointers and several other methods to make sure that you can safely allocate and destroy objects without creating segmentation faults.
Thank you very much.